So let's start by solving the quiz, and after that I will actually start the new chapter. Right? So we are not going to be dealing with capacitors, resistors, circuits anymore. But let's solve this quiz first. So I have two capacitors which have equal charge but opposite polarity. So I have plus Q and plus Q charge in both capacitors, but the way I actually put these together, I could redraw the circuit in a quite different way. The polarity is like this: plus Q, plus minus Q. I don't know why I'm writing with such a coarse pen. And here's my resistor. So as time goes on, what do I know? I know that if I think about a surface here, the net charge inside the surface is not going to change. What's the net charge in that surface? 0. So it means finally, in the final state, my final net charge will be 0. The capacitors, both of them, will be uncharged finally. Okay? But let's do the following. Let's actually denote this I as a function of time. Now, clearly, whatever current is coming out from the first capacitor, the same current must be flowing in all my circuit, right? So this is also going to be I. This is also going to be I. Now, I can maybe say this is going to be Q1 of t. This is going to be Q2 of t, the charges on the capacitors. But what is I of t? I of t, because it's leaving the plus terminal of the first capacitor, must be d Q1t dt. What's the sign? Is it plus or minus? If I have a positive current, it's coming out of the positive terminal. The charge on my capacitor must be decreasing, so there is a minus sign here. But this is just as well d Q2 dt. Right? It's again the same current is actually leaving the second capacitor. So I have only one equation. That's the definition of my current. What else do I need? I actually need to use Kirchhoff's voltage law for this circuit. What's Kirchhoff's voltage law? Let's say that, let me get a different pen color. So I'll start from here and follow the circuit along this route. So the first jump will be across the capacitor, and am I going higher up in potential or lower in potential? I'm going from the minus terminal to the plus terminal, right? So here, when I first cross my capacitor, what will be the potential difference? It will be plus Q2 of t divided by C. So I'm already here now. I crossed the first capacitor. If I cross the second capacitor, am I going up in potential or down in potential? Up, right? I'm going from the minus terminal of the capacitor to the plus terminal of the capacitor, which is at higher potential. So I have minus Q1 of t divided by C. Now I'm here. And I'll go back to my original starting point over the resistor. Here is my current. Am I going to go down in potential or up in potential? I'll go down because I'm in the direction of the current. That's the direction current is flowing, I said. And current must be flowing downhill, if you want. Right? So it must be minus I of t times R. But from the first equation, I can also say the initial conditions for Q1 and Q2 is the same. They are both related to current, so Q1 must be equal to Q2 at all times. Okay? So maybe I can write, okay, so this is Kirchhoff's voltage law. I'm going to write it in a different way, I'll say 2 Q1 of t divided by C is I of t times R. Is there a correction, a comment? No? But now I know what I of t is. I can replace it here. Let me get a more visible pen. So I can say d2 over RC Q1 of t is minus d Q1 of t dt.
Can you use directly capacitor equivalent?
I'm going to talk about it so we can actually write this in terms of the equivalent capacitance of these two capacitors in series. Okay. Now, here it's actually not going to be very hard. This is the one and only differential equation we know how to solve, right? So, what is the solution? Q1 of t must be some a e to alpha t, which means dq dt is alpha times a e to alpha t. If I plug this solution in, 2rc a e to alpha t is minus alpha a e to alpha t. A is cancelled. I, not surprisingly, find that alpha is minus 2 over rc. How do I find a? Q1 at t equals to 0 is small q. That's where I start from, which is a e to 0, which is 1. So a is q. In other words, I found the charge on the first capacitor as q e to minus 2t over rc. I think that was actually part B. So we've actually done part B. We also have to talk about the current in the circuit as a function of time. So what is the current? We've already found written down the formula. This was minus dq1 dt. So if I take the derivative, minus derivative, I'll have 2q over rc e to minus 2t over rc as my current. And it's actually good idea to maybe write down the circulation of the current. Although I've shown it on my diagram here, I did not really specifically state it. When you solve a question, it's easier to make it gradable, easily gradable. So I'll write this current is counterclockwise in the circuit. All right? And finally, what's the time constant? Well, time constant, how did we define the time constant? The time constant was in the exponential factor e to minus t over tau. That sets the time scale over which my charge decays. And by just comparison, I can see tau is RC over 2. That's very important. It's not 2 over RC, it's RC over 2. And does that make sense? It makes sense because, as your friend suggested, when I have two capacitors tied in series, and here, although when you maybe initially look at the figure, you may think, hey, these guys are in parallel. But when I redraw the circuit, you see that when I take care of the polarity, they are more like in series. So what's the equivalent capacitance of two capacitors in series? It's C over 2, not 2C, right? It's just the opposite. So this C over 2 here is the equivalent capacitance which determines the time constant of the circuit. Okay? Any questions? No? Okay. Then I have an important question. Is there anyone here from Manisa? One person? No one else from Manisa? No? Now I can see that you're all intrigued why I'm talking about Manisa. Do you know the ancient name of Manisa?
Magnesia.
Okay, good. So, Magnesia. So, Manisa was Magnesia. And it turns out there were stones in Magnesia which actually attracted each other. Because these Manisa stones, they were called magnets. Okay. So there was a whole study of these stones which was called magnetism. So if you're from Manisa, you're uniquely suited to study magnetism. Okay. Even if you're not from Manisa, we're all from Turkey. Well, we're not all from Turkey, but we're in Turkey. So this is sort of the land where magnetism was discovered by the ancients. Unfortunately, it was not explained by those ancients. They sort of decided that it was some strange magic. There were a lot of people claiming that they can actually communicate with magnets. They believed if you take two magnets, first, you stick them to each other, wait for a while, say some prayers. Then when you separate them in different cities, they still keep the connection. So you can actually point out, you can communicate over long distances using magnets. The guy to disprove such communication was Galileo. He actually tested one of the people who claimed he can do this long distance communication. Which is funny is that 3 centuries later, when telegraph was invented, that's pretty much what we do. We have a magnet here, and there's another magnet. We just have to lay a cable, and even now we don't even have to lay a cable, right? But we do communicate over long distances using electromagnetism. Now, so the simplest theory for magnetism is that you have these magic stones which attract each other. Okay. And the funny thing is, they seem to have a polarity. So they have two poles, and not people from Manisa, not the ancient Greeks, but ancient Chinese discovered something even more important. They said, hey, these stones seem to know which direction north lies. So if you actually suspend them by a string, they always seem to point along the north direction. All right? So that's why they said the direction that points along the north, we call it the North Pole. It shows the North Pole. Okay? But there were, people did a lot of experiments with these. They were playing with these stones. One thing they tried to do is, they tried to isolate the North Pole and the South Pole of a magnet. So they took a hammer, cracked the stone. Unfortunately, when you crack the stone, you don't get a North Pole and a South Pole. Instead, what you get is smaller magnets. Okay. So this is kind of different from electrical charge. We'll see that there are a lot of similarities, but there is a lot of difference in magnetism. There is no magnetic charge. There are no magnetic plus charges. There are no magnetic minus charges. It will always be two of them coming together. So we will always have magnetic dipoles. We will never have magnetic monopoles. Right? So that's going to be one big difference. And sometime later, people were running experiments with currents now in 18th century, 17th century Europe. They also had this compasses. Now they knew that magnets showed north. One guy noticed something really interesting. If you actually have a wire with a current, and the compass here, you could actually change the direction of the compass. Okay. So he made an important discovery. He said, currents create magnetic fields. Another guy, he did the reverse. He took two magnets, so there's a lot of magnetic field here, and then he actually put a wire between them, and he noticed that there is a force on the wire. Okay. Then he stated the reciprocal principle, if you want. Magnetic field applies a force on currents. So now we're going to study both of these principles. First, we'll sort of define the magnetic field by its action. Its most important action is going to be these forces it applies on charged particles. And then the next chapter, we'll talk about how to create magnetic fields by running currents through circuits. All in all, I'll tell you a little bit, so we're going over the history of this. Maxwell realized some more important things which we are going to study in this course, that when you change magnetic field, it creates an electric field. When you change electric field, it creates a magnetic field. And what we call light, or all kinds of electromagnetic wave, is half electric field, half magnetic field. And after a while, almost 70, 80 years later, Einstein discovered something even more important. As you see, electric fields are there even for static charges. Even if all my charges are sitting there, I still have electric fields. When charges start to move, as in currents, then I start getting magnetic fields. All right? So Einstein asked a very simple question. He said, hey, you're telling me that if there's a current on a wire, I get a magnetic field. But what if I am moving at the same velocity with the electrons moving in the wire? In that case, in that reference frame, I would have no current, which means I should get no magnetic field. Then he realized something. The definition of electric field and magnetic field depend on the velocity of the observer. Okay? So electric field and magnetic field can, if you want, turn into each other under relativity. So if you have a friend who is moving at half the speed of light, he would measure different electric and magnetic fields, and you would measure different electric and magnetic fields. So that's why maybe we should view this object as a more compound object, not separately an electric field or a magnetic field. That's why we talk about the electromagnetic field. Okay. So this was the first unification in physics. Two things which look like separate entities are actually sort of two sides of the same coin. Einstein was so happy about this result, he spent the rest of his life trying to unify gravity with electromagnetism, which didn't work. It doesn't work still to this day. Okay. But nonetheless, it's quite interesting. And let me tell you, let me come back to our original stones, right? They are not very good magnets, these stones from Manisa. Right now we have much better magnets. Actually, for 5 liras you can buy extremely strong magnets. They are so strong that you can actually break your finger bones with them. If you get too strong neodymium magnets, you can break your finger bones. Some guy in our lab did that with permanent magnets. And it's very interesting that still the study of what makes materials magnetic is very hard. There is no fully complete theory. So we can do a lot of things about materials, but it's very actually hard to come up with some compound when crystallized will give you a strong magnet. Much of that is still trial and error. Okay. And one thing that's really interesting, if you really want to understand magnetism, you need to learn quantum mechanics. I can tell you, and I will tell you, all these cartoon Mickey Mouse pictures of what magnetism is. Let me give you a spoiler. I'll tell you that all magnetic field is created by current. So how come a stone from Manisa, how does it create a magnetic field? And I'll say, in these Manisa stones, there are circulating currents inside each atom. So these currents inside the atom create small magnetic fields. They add up. That's the special thing about Manisa stones or a piece of iron. Those currents can add up, so they can create big magnetic fields. That's how permanent magnets are made. But to fully appreciate, to fully understand, or to fully calculate what goes on in, let's say, iron, you need to learn quantum mechanics. So that's a even harder job. So let's come back. Let's actually define magnetic field. And I'll do this a little bit differently from your book. I'll start by forces on a moving charge. So how do we know that magnetic field exists? Because it actually creates some forces. I said it creates forces on permanent magnets, or it creates forces on currents. But maybe the purest definition of magnetic field is that it actually creates a force on moving charges. Okay. So here is the thing. So the observation is the following. If I have a charge q moving with velocity v under some magnetic field B, there is a force on this charge. The force on the charge is quite interesting. The force on this charge is always perpendicular to the velocity of this object. It actually is also perpendicular to the magnetic field. And it's proportional. So if this is charged, there is a force. If I reverse the charge of the object, the force also reverses. So it's proportional to the charge. So an uncharged object does not see such a force. How do we generate vectors which are perpendicular to two vectors? Cross product. Great, right? That's why we learned cross product. So the force, the magnetic force, is Q V cross B. Right. What does that mean? Let's talk about. Let's say that I have a magnetic field, a uniform magnetic field. And I'm going to show it by these circles. And here's my notation. You probably know this. What do these crosses mean? A circle with a cross is into the page. A circle with a dot is out of the page. So here I'm assuming there is a uniform magnetic field into the page. Questions? So what happens if I take a particle, let's say of positive charge, and give it velocity v? Let's find the direction of the current on this, direction of the force on this particle. So what do we need to do? Force I know is going to be q v cross b. This is a time to remember how we did cross products. So b is into the page, v is like this. How did we do the v cross b product? We take our 4 fingers, point them along the first vector. I still have the freedom to orient my palm, but I orient it in the direction of the second vector, which is into the page, b. So when I close my fingers from the first vector to the second vector, my thumb shows the direction of the force. So which way is the force here? Up. Okay. So q v cross b gives me a force which is up. So if this particle feels a force, what is it going to do? Is its speed going to change? Let's think. How much work does the magnetic force do on the object? Do you remember the power transferred to the object? If I have an object with velocity v, what's the power transferred by a force? F dot v. F dot v. So this is going to be q v cross b dot v. What's the dot product of two vectors which are perpendicular to each other? The dot product is 0. Why? Because force is perpendicular to v. Which means the kinetic energy of this particle is the same. So magnetic force does no work on the particle. Oh, that's also an important principle. Because, but what does it do? The speed of the particle is the constant, but is the velocity a constant? No, it's not. If I'm moving towards you and there is a force that's actually to the right, what will I do? I'll turn. I'll start turning, but the force is always turning with me. So what kind of motion do I expect from this particle? It will go around in circles. Okay. So before we do that, let me talk about the units here. What's the unit of magnetic field? Clearly, from this formula, it must be the unit of force divided by unit of charge, the unit of velocity. So it's going to be newtons per coulomb per meter per second, Newton second per coulomb meter. Not a very good unit, right? You don't say Newton seconds per coulomb meter all the time. It's given a name, just like any other unit in electromagnetism. It's given the designation Tesla. So I think the car company was very clever. They get free advertising in Physics 102. That's not a bad joke. Come on, I can do better than that. Okay, so it's a Tesla. But so I mean, let me give you a sense of this unit. Tesla, it turns out, 1 Tesla is quite a lot of magnetic field. So what's the order of magnitude of Earth's magnetic field? There's actually a separate unit of magnetic field, not an SI unit. Earth's magnetic field on the surface of the Earth, Earth, is called more or less 1 Gauss. Okay, that's another unit, which is 10 to minus 4 Tesla. So this is 1 Tesla is 10,000 times larger than Earth's magnetic field. So to create 1 Tesla in a small area, you need electromagnets of pretty much this size. Okay? To create 5 Teslas of magnetic field, even in a small region, you need huge electromagnets with probably cooling. The highest magnetic field we can generate in the lab is 100 Tesla. That's our current capability. We do not have machines to create 1000 Tesla. So Tesla is kind of a big unit. Okay, generally when you go into the lab, it's millitesla. Millitesla is a big magnetic field. All right. Now let's go back. Let's talk about the motion of this charged particles. What does this charged particle do? Is there a question? No. So my charged particle is moving with velocity v, feeling the force F. So what will it do? It will actually do uniform circular motion. All right? Let's try to find the radius of this motion. So turn this into an example. What's the radius of the circle my particle is going to trace? I also would like to find out what's the period of the motion. Well, it's not too hard. If I'm doing uniform circular motion with velocity v, what's my acceleration? Come on, physics 101. V square over r. So this v square over r acceleration, m times a, must be supplied by the magnetic force. mv square over r, I have them in the same direction. So F magnitude is q v times b. Why am I so sure of that? Because v and b, v is in this plane, b is into the page. So they are perpendicular to each other. Cross product gives me just their magnitudes, right? So good. So the radius is m v over 1 power of v cancelled, q times b. Does that make sense? Let's think about this. If I have more velocity, I trace out a bigger radius. It kind of makes sense. I mean, it's hard to turn if you have a lot of momentum, and that's actually good. What I have is mv, right? In the numerator I have mv, so I have actually a lot of, if I have more momentum, then the radius would be larger. It's harder to make a turn. How about if I increase the magnetic field, I go in tighter circles? Does that make sense? That also makes sense. Good, because I have more force now. How about the period of the motion? Well, what's the period? Time to complete one circle, right? So the total length I have to travel is 2 pi r. My velocity is v, so it's going to be 2 pi mv divided by v qb. V is cancelled. So it's going to be 2 pi over qb over m. Wow. It's kind of strange. It doesn't depend on the velocity. For example, if I have a particle, an elementary particle or a composite particle, it suddenly explodes. Okay, let's say that there is a chemical reaction or some nuclear reaction. So many charged particles come out of it with different velocities. If I'm under a magnetic field, I'll see something very interesting. I'll have, let's say, a particle with charge q, an electron with velocity v, another electron with velocity v prime. They will both trace out circles, but they will come back to the same point at the same time. So if there is an explosion, one period later, all the particles will come back to the same point. So that's very strange. That's very interesting. Actually, so I can write this as 2 pi over omega, and I'll call it omega c. Omega c is qb over m. The frequency of motion is independent of velocity. This is called cyclotron frequency. Do you guys know who cyclotron is? Come on, you don't watch Transformers? Megatron, Optimus Prime, cyclotron. Some of you are not sure even if this is a joke. Okay, so it's, okay, obviously it's a joke, right? It's okay. So the cyclotron is the first particle accelerator. And let me, you know the particle accelerator at CERN, LHC, right? How big is that? It has a 4-kilometer radius. So it's a pretty big object. The first particle accelerator, the cyclotron, could fit in your hand. And it got to the electrons to 0.9 of light velocity. Okay, so it's a pretty nice device. Let's take a 10-minute break. When you come back, I'll tell you how this cyclotron works. And we'll talk about other things about magnetic field.